Hello YouTube! The episode I had before briefly described how style transfer works, and if you haven't seen it already, you could take a quick look at it. And if you've already seen it, then we're ready to go. So just like every other video, every other program, we're going to import our dependencies, which is Tensorflow, as we know, matplotlib, numpy, and a few helper functions that I made. One is used to just pull images from the file. It's also on my GitHub, so you could use that as well. And a plotting tool. Super simple, just saves me to write a few lines. And I use them often, so. And also we're going to be using the Oxford VGG19. So this is conveniently located in Keras under applications. You could just download this. It'll take a few minutes maybe, but after that it'll be clean every time after that. So with no further ado, let's write our code. So we're just going to start off by specifying the location of my style image. And this could really be anything you want. But for me, I am going to be using the wave, the Great Wave image, which is a very famous painting. You've probably seen it before. And kind of like the standard when it comes to style transfer. Everybody likes using this image. There it is. Giant wave. Okay, and I'm going to be using my content image, which is a picture of the Golden Gate, which a friend of mine took a few weeks ago while we were at Google Next. Kind of became my go-to image. But this could really be anything. This could be a picture of your face, or it could be a picture of your girlfriend's face, like I did. Yeah, make her eyes into stars. So there's an input layer that just takes in an RGB image, which means it has 3 channels, and with unknown width and height, and unknown number. So this right here would be the number of images. This right here would be the height, and this would be the width, and this would be the channels. And we go on. This is a convolutional neural network, so it takes in a convolution with 64 filters. This would make 1792 parameters. And you can see that there is no top. So you see there are no dents. There isn't the dense head that would bring you the one hot like vector at the end, which would be used as classification. Okay, so for just clarity's sake, we're just going to set style image equal to the wave image, because that's going to be our style. And the content image is the Golden Gate image. Network does a few things to it. Firstly, the VGG19 will take the image and scale it according to a set 3 numbers. So you'll have a average red value, an average green value, and an average blue value, right? So RGB, and subtract every pixel's RGB values by those numbers. It'll also flip the red and the blue, so that we have BGR instead of RGB. And so it'll be processed, pre-processed. So we could say processed wave, if you want to take a look at that, equals VGG19. But we're going to do pre-process input, which is a function that's available with VGG19. And we're going to expand the dimension of the 0th axis of the wave image. So this image has only width, height, and 3 channels for RG and B. But we also need the number of images to be 1, namely. And so we're going to be adding that axis. And so we're just going to be saying that expand this input around the 0th axis. So instead of being width, height, channels, it'll be 1 with height channels. So there's our processed wave, and we can just take a look at the shape. And we can see it's 1, 512, 512, 3, as expected. Okay, and if you want, we could take a look at it. And we see that it's, firstly, the colors have been flipped and also the colors have been subtracted. That's why you could see the clippage. So everything that's below 0 has been opted to 0. That's where you see the black, and everything that is above 255, or rather above 1 in this case, because they're floats, it becomes 1. Right? And so this is what this says: clipping input values from RGB 0 to 1 for floats and 0 to 255 for integers. The reason why we have white here is because when we subtracted the VGG19 biases, we turned the integers from integers to floats. And so once it was 0 to 255, but integers, and we subtracted it, and now it's negative something to positive something, above 1 and below 0, but now they're floats. And so you could see that all these pixels have been clipped. That's what this is saying. Okay, let's keep going here. We're going to do the same thing for the content. And again, we see 1, 512, 512, 3, as expected. So we know that the VGG19 does some pre-processing, but when we get an output of our image, we don't want it to be pre-processed. We want the real image. So we have to do unprocessing. And to do that, we need to know the biases, and we have to flip the blue and the red channels to be red and blue again. And so we're going to make a function. We're going to call it naturally deprocess, and VGG biases and we're going to get the values out of here. So the way we do that is we just get an array of 3 zeros and set it to be as type. So what it'll do is just process these 3 zeros. And once it's processed these 3 zeros, we could see how it's been added or subtracted, right? So we're just getting one by one image with 3 channels, which is RGB. And so we have the VGG biases. The VGG biases are -103. It means that it subtracts 104 around from the red channel, 117 from the green channel, and 123.5 from the blue channel. Or flipped. So the blue channel is subtracted 104, green 117, and red 124. Okay, so now we have that. We could take the unprocessed image, be the processed image minus the VGG biases. Actually, I think I want to call this deprocessed images. And deprocessed image, we're going to unstack the unprocessed image, or rather deprocessed, around the last axis. So the last axis is the channels. So we're turning the 512 by 5, the 1 by 512 by 512 by 3 image or tensor into 3 1 by 512 by 512 tensors. So we unstack them and then we stack them back on. And that's what we're going to do right now. So we want the second channel first, namely the red channel. The green channel stays where it is, and the red channel stays where it is. There might be a better way of doing this, and if there is a better way of doing this, please feel free to put it on the comments. I'd be happy to know. And of course, we want to return the deprocessed images. Okay, so now that we have that, we can check it, right? So we say, let's just plot it. What's that? Right. Still. Oh, right. So these would be all floats again, right? So we want it to be back to ints so that we could so that it chooses the right setting. So instead of going from 0 to 1, it goes 0 to 255. Okay, so we see that we deprocessed it and it looks pretty good. So we're going to keep going. So if you haven't seen the video before, you should definitely take a look at that, but I'm just going to quickly rephrase. When we take style transfer, when we do style transfer, we want to take certain elements of this network. So we don't want the output, we want certain layers, right? Certain layers to be our inputs to our content loss and our style loss. So I'm just going to say the content layers, and we're only going to take one, and I want it to be one of the last ones. So let's just say block conv2 will be our content layers loss. So that'll be the layer that we'll be using for our content loss. And our style layers going to be, I guess we should use all of block 4. So I like not using the very last layer, because this layer kind of takes out all the content. But I also don't want to be too early, because then it's not really illustrative of the style either. It's not general enough. So sometimes I just pick the second to last or third to last. You could try block 3 or block 4. It's all up to you, and it's fun to play around with. So I'm just going to pick block 4, and I'm sure there's some theory about this, but and we're just going to pick all the convolutional layers. So I guess it's 1, 2, 3, and 4. Okay, so that's our style layers. Now we're going to make the model such that it spits out these layers. So I guess we want it to be so include false, and we'll also give it an input shape if we want it to be that. I suppose we actually don't need either of these things for now. Let's just make the model, right? So I'm just going to call it base model because it makes sense. It's not the same base model as before. So VGG19, we're going to make another VGG19 network, and it's going to not include the top. So include top has to be equal to false. And the weights have to equal weights that were made from ImageNet. Well, it doesn't have to be. You could choose whatever you'd like, but that option is available to you. And we want none of the parameters in this model to be trainable, because we're actually going to be doing gradient descent on the image, not on the model. The content layers are equal to the content layers, and the style layers are going to be equal to the style layers. The output layers are going to be the mix of the two. So we're going to do some list comprehension here. So we're going to get the layer from the base model. And we're going to be using the TensorFlow models API. the Keras models API, which allows you to take in an input and output whatever you say here. So we can take in an input of the base model, not models, model, and output the output layers. And there we go. So let's instantiate one of these now. Okay, it's a model, not models. Yes. All right, now we have a model. Okay, so now we could check it out, see if it works. Let's do it on the Golden Gate. And you need to input the processed image, so processed Golden Gate. And we'll do it for the wave as well. And we could set the Golden Gate content to be Golden Gate outputs, and it's going to be the 0th element because we put in the content layers first. And the wave content is going to be wave outputs 0, although we really don't care about that because the wave is kind of the style, right? But no matter. Actually, maybe we'll just delete it. Okay. Now we're going to make the content loss. And as said in the previous video, the content loss is just the L2 norm, the Lebesgue 2 norm of the image and the content. Okay, so what I mean by that is just the standard Pythagorean norm, just x squared plus y squared square root, right? But you do it for all the different dimensions. You can take a look at the previous video if you want to understand that a bit more. And that's it. That's the whole content loss. So basically we just take the content of the new image, basically the image that we're producing at every time step, and subtract it from the image content at the next time step, or the base content. So just the normal image, the regular image. So in essence, what we're trying to do is keep the content the same, recognizable. So if there's a turtle in the original image, it'll still look like a turtle in the processed image, or in the image after each time step that you run it through the algorithm. All right. Now we have to do the style loss, which is a little bit more tricky, but not that tricky once you get it. So we're going to be producing a gram matrix. And if you don't know what a gram matrix is, you could also take a look at the previous video. So what we did here is essentially taken a layer of the output. So each one of these has, for our case, 4 layers, and we took one of those for each of them. And in each of these, there are a number of filters. And what we did is we did a matrix multiplication of each of the filters after processing of the filters. And the transposition just lets you do this matrix multiplication. So if you have like an n by m matrix, like style layer, and another one that is style layer n by m, you can't multiply them. Matrix multiplication requires that the second element of the shape of the first element is the same as the first element of the second. So then we took the gram matrix and normalized it by dividing it by n and spit out n at the same time. So we spit out normalized gram matrix, and we could take a look at one. Voila. So this, in essence, is the style of the image, one of the elements of the style of the image. What is really cool about this is understanding that the style is represented by the relationship between the filters and not the filters themselves. So how the filters interact with each other rather than the content of the filter itself. All right, and so now we could get the style loss. So we want the new image style, so the style at every iteration, and the base style from the original image. So the new style, gram matrix, and it puts out a height as well, the size, right, which is a square matrix. It doesn't matter which one I take, the width or the height. I'm just going to take the height. And we get gram matrix. We're going to input the new image style. Okay, but that's not enough. We need the base style as well. So we take the base style and gram height 2. It's a stupid name, but forget about that. Okay, so get gram matrix, and this could be the base style. And at this point, we have to assert that the gram, so this is just for safety. We're just making sure that they're both the same size so that we can subtract them correctly. Right, so the number of features is the shape, so the size here, which I suppose you could just set to gram num height. And the loss now is just the sum of the L2 distance between them. So just like before, we subtract them and square them, and then we divide by a factor seen in this equation and explained in the last video, I mean. And then we just return the loss. Of course, I said this. Okay, and so now we have the style loss. And now we need the total loss, which is the product of both the style loss and the content loss. So we input a new image, output, we supply a base content, image output, a base style, image output, and a scaling factor of 0.999. So this right here just tells us how much we care about the style versus the content. And this is largely based on how big the style loss is compared to the content loss. Great, so now we have the total loss. Let's see if it works. All right, good. Okay, so now we make the base style. So now we're going to do the actual training. So the base style outputs is going to be equal to the base model with an input of the processed wave. and the base content output is going to be equal to the base model, the processed golden gate. Now, what we're going to be changing through our training is the content. So the processed content variable is going to be equal to variable. So doing this allows us to iterate and train over it. So it's a processed gate, golden gate. And we want to add a little bit noise so that we get some interesting results. You don't need to do this, but adding noise sometimes helps a little bit. So it won't do much of a difference. We're going to be using the Atom optimizer. And these are some Atom parameters. So it's how we will choose our learning rate. So initial learning rate is 5, and these other features you could... this video isn't long enough to explain. So to observe our training, we're just going to be using a display so that we could clear our output and not just get this long list. Make a list for images so that we can make an animation later, and the losses for each of these images. Excuse me. And so we will begin training. There's a global I, which is the number of steps we take. There's a best loss, which I'm going to be setting to a big number, so that we know which one is the best image so far. I'm going to set a minimum value, which is the minimum biases. So 0 plus VGG biases is the minimum. And the max values, which is 255 plus the biases. And then I'm going to do it over 50 steps. And we're going to be using gradient tape, which allows us to automatically differentiate our losses with respect to our variables. So our loss, our total loss with respect to our variable, which is the image processed gate. And we're going to be watching it. This is, we haven't yet said what we want to watch. And then we want the outputs of the image. So we put the image into the base model. The loss is, of course, the total loss now. And then we will apply a gradient to the optimizer. So we need to zip our gradients and our processed content variable. So this gradient will have a gradient for every variable in processed content variable, and it'll go through an optimizing step. In this case, it's Atom, but it could be stochastic gradient descent or RMS prop or whatever. And then we'll output a new, well, it'll set processed content var to a new value. And we want to clip it so that we can't get above or below a certain value. so that the image is still recognizable. And we want to assign processed content var to clipped. And for every 5 steps or so, we want to append the image to images so that we can see them later and make a slideshow or a animation. And then we want to also, if the loss is less than the best loss, then it's the new best loss. So the new best image is the current image. So the best loss is now loss. And to just make sure we're not going insane and it's actually decreasing, let's just display loss and clear the output. And we want to wait for a new value to come along before it removes it. All right, so also let's just stick this together because I wouldn't want to run 3 cells for one operation. So let's just run it and see if it goes through. Hopefully it goes through. And we could see that it actually does good work. Okay, I stopped it because I don't want it to take forever. Now we could deprocess the best image. Remember that this image is still in VGG 19 mode. And we could plot it. Okay, so I'm just going to skip forward to the animation. I'm going to run this for a few hundred iterations and show you an animation. So after around 30 minutes or so of training, we get this one. And it's around 10 seconds long. So I'm going to run it. Yeah, and that's it.